you're ready to go. What I'm going to do is go through testing today. This is very similar to what you get on your LEP board. If there's other things I want to make, not just testing of this because you've got to learn how to do it with a set of mega leads, but also putting a little bit of explanation around different things. So first thing I'm going to run through is the meter you've got to use is like a Keiretsu or moving meter. Analog, you can't have a digital meter. The other thing is the difference between the two. When we do anything in the blue, it's continuity. Continuity is for things like when we test the mains, okay, so one of the requirements down here is continuity of the mains. We don't need to pump 500 volts through it, we only need to pump, just a couple of volts, but the continuity through it to make sure it goes from A to B. We would use a trailing lead for that. In part of the SWP now, they're asking you to establish the earth with a trailing lead. And people, it looks like it's a whole new language to them, but really when you do testing of an insulation, you use it more than the earth. Now, some of the first tests that we've got on this, on our test sheet, you don't have to follow it in their order how it's got it laid down. You can do it in any order you want, all right? How you test the installation is up to you, but as long as the results come in and they retain what the results match up to what they've done on their board. Anyway, everything's mostly below 32 amps now today is RCD protectors, so it includes stoves, hot waters, everything like that. The main thing when you're testing insulation, you want to remove the things that can create a problem in testing. Not that they would be faulty, but we're testing the insulation wiring. If we're going to do the hot water service or the oven and all that, unplug them and remove them out of the circuit. Do you understand what I'm getting at? We only want to test to the plug at the moment. If there's a problem, we then test them individually, like we do within the appliance down here. Okay? Trailing leads are also used for, for example, testing the main earth, testing the bonding earth all the way around the property. So with a trailing lead, I would have one of these attached to my main earth, and the other one would be a 20-metre lead. The main thing we have to do with that, like the SWP, is zero it out. So we would select that to 3 ohms, join the trailing lead and the other lead together, and we remove that resistance of that lead out. That's all you've got to do. Once you've done that, and then you go around and take the readings of all your earths, so the bottom line is you don't want to be adding the resistance of the leads to your trailing lead to the readings and then being out by 1 ohm or 2 ohms, whatever the resistance is. All right. So, as I said, you remove all your appliances. Make sure that there's no electronic dimmers as well. That you're going to pump 500 volts in there for an insulation test. The dimmer might not like it. Does that make sense? So you remove that or bridge them out, whatever they want to say. Make sure all your switches are on too when you're doing the whole installation. That's something I talked about yesterday. Because you will need to test if you've got twin active down the wall or anything. We need to be testing all of the wiring in the installation. Okay? Somebody said to me yesterday, if I had a short between active and neutral on a twin TPS, would that pick it up? Yes or no?
Yep.
No.
Shouldn't it?
No, because it's on the same wire. It's on an active wire. Do you understand what I'm getting at?
Yeah.
For us to pick up a short, it has to be short to earth, right, or down to earth. When we do an active and neutral, the only thing something like that would do would create a light to stay on or something like that. So don't forget on a twin active, if you've got a short on that, it's not necessarily going to pick it up. All right, unless you break the twin active and do an insulation test between the two conductors, that's the only time you might pick it up. All right, so you've got to be careful when you're doing tests like that. Okay, the first test we're going to do when you look at 8.2 is you have your earthing. So when you look at the flow diagram, that's what I'm telling you to look at. If you're not sure, pull your reg book open and that'll give you a start. The main earthing conductor, right, which we have from here down to, this one down here, the earth electrode. Then we have a bonding conductor. A bonding conductor and the main earth are two different cables, all right? They're both the same, but in other words, I get people sometimes saying, oh, I'll run the main earth to the tap because it looks like a bonding conductor and then going to the main earth. You can't. You've got to go from the main earth, right? Either run them separately or you go to the main earth first, then to the tap. Does that make sense? Yes or no? The main reason is if you take the bonding conductor off the tap and then remove it, and their main earth is not hooked up. It's disconnected out of the circuit. All right? What's the problem with tapware these days? What's the problem with taps these days too? Exactly, there's no continuity of copper or anything. We don't have the continuity going into ground or whatever you want to do it. Our earth stake will go in. Another type of earth we got is the strip earth, okay? If we have a strip earth, do we have to do, how do we do a test then? It's all quiet. You can't do a test on a strip earth, all right? The problem you got with that is because it's in the ground, right, there's no connection point. What we're doing here is from here to this earth electrode is just making sure we don't have a high resistance, all right? So a strip earth is very hard to do a test because it's buried directly in the ground, unless you've got some point where it's open and you can do a continuity test, that's it, all right? So there's no connection point, there's no tag to be put on a main earth, a strip earth, I should say, but we have to have a tag like this down here that we don't remove it. All right, so earthing's the main thing we have to establish on doing an installation first. Once we have all our reference points done and pick up what's not earth and earth, then we can head off. So the first two is the main earth, all right? What's the first test I need to do? When I'm testing I've got this meter, got down the truck, what's the first test I've got to do?
Zero.
Sorry? Battery check. All right, I want to make sure my battery's working correctly. So I go to my battery check down here, push my button in. That's reading, pumping up nice and strong. I'm happy with that. The next one, I go to zero my meter out, all right? Some leads you get, you might have the option, I'm just showing you on this, we've got a clamp so you can actually take this out and put the clamp in, right? Or you might have the probe, okay? The only problem is when you've got the clamp, if you have to test into a power point, you won't be able to use that, all right? So you can either do it at the switchboard end. All right, so the first thing I'm going to do is short my leads together. I read zero. When you're looking at a meter to zero, I'm not probably looking at it here. It's better to look at it down on a bench and looking over the top of it. Do you understand what I'm getting at? If you start looking from the sideways or this or that, it might not be quite on zero. So I'm looking at it from here. It looks like it's on zero, but when I go to the front, I've just got to give it a little whisker and I'm done on zero. Now I've zeroed it, I've taken the resistance of my leads out. If this lead was a 20 metre lead, I would have now removed the resistance of that 20 metre lead. Okay? All right, I've zeroed it out. The first test I'm going to do is go from my main earth, all right, down to my earth stake. Do not go to the clip. Why don't I test to the clip?
Because that's not the part that's in the ground.
Sorry?
That's not the part that's in the ground.
That's exactly right. So I need to test to the earth electrode, all right? I'm getting nothing there. That tells me that I've got an open circuit, there's nothing there. Now I'll go from the main earth down to my the earth bar to my bonding conductor. I've got a reading here, it's about 0.1, that's okay. So on your sheet, you would have that the main earth is an open circuit, all right? Don't write infinity because you're not measuring voltage or anything, all right? Just to say it exceeds the 0.5 ohms, right? It's not reading, not reading anything, it's reading nothing at all. So we go down to there again, it's reading more than 3 ohms, it's an open circuit. Are we all happy with that? All right, I've done those first two. The next one I'll talk about is jump down to where it says testing of all subearths. I'm pretty sure. Down there, got insulation resistance, testing of appliance, testing of protective earthing conductors. The reason I say to go down into that is to get all the earthing out of the way. Does that make sense? So on that sheet, they would have given you the size of the breaker, the resistance of the active, right? We're actually doing a test similar to what we do on the last test. The last test we do is fault loop impedance, right? This we're kind of doing is like the same as fault loop impedance, but they're actually giving us the active conductor size. Do you understand what I'm getting at? So once we work out the earth's, all the earth resistances, we then add them with the active. We go to our book, table 8.2, add the two together and see if it exceeds that value that's inside the book. So I'm also going to establish that all my earths are correct. So I'm going to go from the earth bar over to here, beautiful, and I start working my way through all the earths. And I get down to here, I might get down to this one, beautiful. I got nothing here. So socket outlet number 3 doesn't have an earth, okay? I can write that down. I get up to socket number 1. So as long as I'm getting a reading, okay, just put that up here. So I'm establishing all my earths up to my earth bar, and I'm getting high readings, more than probably 1 or 2 ohms. So they're going to be ones that are going to fail. Make sure, does it make a difference if I have my light switches turned on for doing the earth? No, that's got nothing to do with it. It's only when we do testing of insulation. So I've done all my earths, written them all down. Now I'm going to come back and test my whole installation. Now, when you test the whole installation, right, the problem is up at the meter box, we have line and load, okay? The line is what goes out to the pit, all right? That's the underground pit. Now, I don't want to be down in the ground trying to put clamps onto on an earth pit and all that. I got nowhere to join to. So the other one is I've got to bring the load, which goes back from here to the main switch. I've got to join that because that's where my current gets read through. Do you understand what I'm getting at? The little neutral we got here, which is usually a smaller size, 4 or 6 mil, that's what supplies the voltage difference. Do you understand what I'm getting at? That's my current running through here. I now need to provide a power. So what I'm going to do is I'm going to bridge all those 3 out, which is an easier place to do. That means I've bridged my active and neutral out. I now have it from the pit. Both cables at the pit are now joined together. I have it all the way back to the switchboard and I have active and neutral. At this point, if I had my MEN in, I would disconnect it, which I have to do, because now we're testing active and neutral to earth, the insulation value. Now, before I did the zeroing on the ohms there and all that stuff, when you select 500 volts, do I select 1,000? Why?
It's too high.
Sorry? Because everything we're doing is to earth, so it's 500 volts, right? Double the pressure. 240 volt to earth. If we're doing 1,000, it's phase to phase. Does that make sense? So when you're testing anything to earth, we just do 500 volts. If you're testing phase to phase, we do 1,000. It's double the pressure. It's all. This is all DC, all right? It's not AC. Why do we use DC for? AC is alternating, right? So as it gets further away, the arc gets weaker. With DC, I've set it jump nearly on a meter, all right? And it's very deadly, all right? If you get, that's why I say to guys working on low voltage batteries and all that stuff with spanners and stuff, be very wary, all right? I've seen somebody nearly get killed on a 24 volt battery, but it had 700 amps sitting on across the terminals, all right? So you've got to be very careful. DC is more, in other words, if you think you're going to pull away and get away from the arc, it will grab and hold you, all right? So we use DC here, it finds faults and finds weaknesses in cables much easier, all right? So I've got to that point. When I push it in and I've got the 500 volts, I need to, if I short the leads together, it goes back to 0. That's okay. But we use something like this, what we call a insulation tester checker. What it is, it's basically putting the voltage under load. So if I go to 2 meg or 1 meg on here, I can put that across my load, all right? And it should come up to 1 meg, all right? So it's putting it under load, making sure you don't grab the leads yourself and get a whack. But that's, instead of 0 in the meter, we use this to actually load it down, all right? And check that what I'm reading under load is correct on the meter. Are we all good with that? All right? Okay. The other thing is now I've disconnected my main earth, my MEN. My earth's done, we know that's, well, we know it wasn't working before, but we're now doing the check. I make sure all my light switches are turned on, main switch and all breakers are turned on, okay? If we had a circuit breaker, all RCDs are on, circuit breakers are all turned on, and that's what it's got, where it's got testing the whole insulation. Where it says consumer mains on that, you probably won't see that. This sheet's a little bit older. On the LEP one, they don't have the consumer mains written on there. They just have whole insulation, circuit 1, 2, 3, 4. We all see that, yes or no? The thing is, we can't do consumer mains because we're actually doing it as part of the whole installation. Do you understand what I'm getting at? So you're not going to do a separate test for that. Okay, got it on 500 volts, all right? I took the wrong one out, put this on. I'm now going to go between the top of the main switch to my earth, and I've come down to 0.5. Is that a pass or fail?
Sorry?
Sorry?
Fail.
Yep. Minimum reading is 1 meg. Any heating elements, metal sheath heating elements like this one, hot water service or stove, they're 10,000 ohms. Be wary, the 0.01, if you look on this mega, sits just above the 0. That's 10,000 ohms. 0.1 is 100,000. All right, I've had people go in the SWP and they've got to read out the reading and they go, oh, it's 0.1 of a minimum reading. Okay, he's writing down 100,000. You probably think it's 10,000, but I always say don't use the 0.01, just use it and say 10,000. Okay, all right, 0.5 is a fail. What's my next step? What do I got to do? See, the silence is killing me. Isolate all the circuits. Turn these off. Why am I isolating the circuits now for? Yes, we can start going back to an individual value. The thing with an RCD is you isolate pretty much the active and the neutral separately. Do you understand what I'm getting at? Unless you want to put a bridge. Sometimes when you're going across and testing, you can have a good active but a crook neutral, or the active's crook and the neutral's okay. Do you understand what I'm getting at? So what I do is, as we go down, I go to earth, I work my way along the top, that's okay, the lighting circuit, beautiful. I've now got a reading down to 0.6 of a meg on the active, 0.6 on the neutral, so both active and neutral on the lighting circuit are affected. I'm getting nothing on the power circuit. So my fault is now on the lighting circuit. If I went to test the whole installation, I could actually turn that back on, leave the lighting breaker on, and I reckon if I go between earth and the other one, it's reading infinity, or 50 meg plus, don't use word infinity, sorry. All right? So that means it's okay, but as soon as I turn that breaker on, I'll actually introduce the fault again, and it'll pull it back down. So I've isolated to the lighting circuit. Things that could also be in a lighting circuit is what? What other faults could I have? If you've got fluoros with ballasts and capacitors, they're ones that create shorts. Most LED lights these days, they don't normally create a short, they just go open circuit or don't work. So you'll find that it could be either crook wiring or something like that, but if we have LED lights and appliances removed, then it has to be somewhere in the wiring. Like I said about the twin active before, I have some people go, oh yeah, but I could have a short in the twin active and it could create a short. It's not going to create a short at all. It's still reading on the between active and neutral to earth. All right, I've done that. I've got my lighting circuit's a problem. Okay, that's all I want to know. The next one I got is my appliance. Like the SWP, before you're going to hook up the appliance, what are you going to do to it? All right? Sorry?
Just the appliance.
Yes. It could be say, oh, some guys come out and go, look, I found this stove on the curbside, great thing, I still want to use it. Are you just going to hook it up? No, you need to test the integrity of it and make sure everything's going to pass and work okay before you hook it up. You agree? Yes or no? It's like a car, you don't take the word of the salesman, you go out and test drive it and make sure it's doing everything what you want to do. So the first thing we're going to do is go back to ohms, going to go back to 3 ohms. I'm going to test between the earth pin and the frame to make sure that I've got a established earth. All right. So between the earth pin here, one thing some kids got caught on yesterday as well. See how the earth pin here's got half plastic on it? Make sure when you're testing to the metal part, not onto the plastic. He said, oh, the earth's not doing this or doing that. I came in and we redid it, and he didn't realise he had the clamp sitting across on the plastic. Do you understand what I'm getting at? So I've done that. I'm going to now go to here. Beautiful. I've got 0.5 of a ohm, probably the value that I don't want to see is probably a bit too high, but at the same time it's still got an earth point to that door there. Now, the next point, I need to make sure can everybody hear that clicking? Hang on a second. Yeah. One thing, I'm not sure, but in the SWP, I've heard that they get an indication when that thing's turned on. All right, so make sure you've got to turn on. Before you do any testing or checking on your appliance in the SWP, turn everything on. Same with the strip heater, 1, 2, turn it on up to high. Don't just turn it on to the first one. You must turn everything on to full value. I've turned that on. I'm now going to switch that to 500 volts. I test between the earth pin to here. Okay, I've got infinity, that's okay. I can also test between the frame if I want to make sure it's at the same reading. A little bit hard to do, but here. And I've got infinity as well. So now I know my appliance is okay. And that's all I'm required to do. Continuity of earthing and the insulation resistance test. All right. Minimum reading on this one.
10,000.
Sorry?
10,000.
10,000, correct. It says metal sheath heating element. So if it has a sign on it and tells you. What about this one?
Same.
Sorry?
Normal.
Normal, 1 meg.
1 meg.
All right. The difference between a bar heater to a metal sheath element is quite a big difference. 1 meg versus 10,000 ohms. All right. Okay. With that passed all right, I've done everything on this front sheet. Turn it over. Polarity of mains. Do I need 500 volts or do I need 3 ohms? I'm going to ohms. I'm not testing if it's got a short or anything, because when we tested the whole installation, all right, it was okay. If I had a problem with the mains, then I would be doing something with the dead short. All right. So now what I've got to do is take this off, leave this on. I'm going to now test it on to 3 ohms. Beautiful, goes to 0. I now got 0 reading. They're not looking for an ohmic value on this. All I want to know is it from A to B, does it pass? Write down the value, but there's no minimum or maximum value, because you know what? I could have 2 metres of mains, or I could have 40 metres of mains, or 100 metres of mains. So you can't really say I've got a minimum resistance. Pardon me. So I'm going to go from here, the top. I'm not getting nothing. Let's just go to the neutral. Okay, so I've got my polarity is switched. Okay, I'm now going to do the neutral. Go to the active. So my polarity is actually switched on the mains. So what I have to do is on both of them write that they both failed, but I would write a little comment that the mains are transposed. Okay, and that can quite easily be done in the back of the meter box. All right, no problem. Especially on the 3-phase circuit, the blue and the black, especially if you're running 4 SDIs, black, right? Black SDIs, XLPE, it's quite often I've seen where the neutral and the blue phase have been swapped. So that's why you've got to make sure you've got the consistency of everything going out from A to B. And that's why they insist on putting colour or heat shrink on all your cables. Do you understand what I'm getting at? Especially if you go through a brick wall or somewhere like that. I used to put heat shrink through so we could identify the cable from one side to the other. It's amazing through 100 mil of wall how something can get crossed over. Alright? Alright. Done the mains. Switching of the switches. So checking correct operation. So all I'm going to do is I'm going to go to my hot plate. Still on ohms. Come down to here to my active. Turn the switch on and off. Beautiful. It's switching. And all I have to do, so the same when I get to the lighting fluoro here, and I get to the lighting circuit, go there, and I'll just turn the fluoro switch off, make sure. And sometimes you might find that it doesn't do nothing, which means the fluoro switch is hooked up to, it's not doing its job, it's not isolating the light. Do you understand what I'm getting at? So if the switch doesn't do anything, the other option you could have also is the neutral could be switching as well. All right, so when you have a look on the paper there, I think it's got active, neutral, or neither. Neither would be like the lighting circuit here, that nothing's switching, and neutral or active, depending which position I've got it in. Are we all happy with that? Last one, automatic disconnection supply. So what they mainly just use it on the, so we're going to just do it on the appliance socket outlet. What they want you to do, you can either use this point here, plug this in, and put a short between the active and earth, right? But I'm going to do it at the switchboard. So what I'm going to do is I'm going to put a, between the earth and the active, I now have the active and nurse shorted. What we're doing is we're measuring the resistance from the bottom of the circuit breaker down to the appliance, back up to the earth bar, to make sure that resistance is not too high on table 8.2 to actually not cause the circuit to work, all right, or operate. You've got to remember what happens as the cable gets bigger. The resistance becomes less. So at the mains, going out back to the start point, all the way through the mains, we don't have a problem because our cable's quite big. The choke point we get is on the final subcircuit. If we don't have that resistance right, it becomes a choke point for our current to operate in that loop to operate the circuit breaker. You remember it's a closed circuit when we get the weakest point for the circuit breaker to work. If this is too high, it's going to choke the current and not allow it to operate. So what I've done, I've gone to ohms, I come down here, I measure, make sure the switch is turned on, and I've got 0.4 of an ohm. I take that value back and I have a look at table 8.2, like we did when we measured the resistance of the earths, and then we added to the active value. Do you understand what I'm getting at? So it's called the RPHE value. All right. The difference with 8.1 to 8.2, 8.2 we're looking for the resistances of the circuit. 8.1 is when the circuit's got 240 volt on it and it's under load. Does that make sense? We all got that? All good. Do I need to explain any more on that? Are we all hunky-dory? Yes? All right. Let's come over to the RCD testing. RCD testing. I haven't got my glasses here, so I'm a little bit blind, but you have 3 RCDs. One will be 10, 30 and 100. But you need to be able to read the information off on the RCD. Normally you'll have C20-6KA. That has nothing to do with the fault loop, the RCD trip value. That's the current value and what we call a KA rating. Usually underneath it'll then say 10 milliamp, 30 milliamp or 100. When you tester we got here, we put in, I'll turn this on. The end button here is what we select. So in other words, if you're going to test a 10 milliamp RCD, there's no use having this set to 100 or 30. Do you understand what I'm getting at? You need to set it to 10 milliamps, all right? Which I think I'm going to down to 500. Now I'm set at 10 milliamps. That is 10 milliamps, I'm pretty sure. Now we have this button over here has 2 things. It has milliseconds and milliamps, all right? So when I push the test button, we go through. It keeps going, might be 20 seconds or not. If I'm right, I might be on the wrong one. But it trips. If it doesn't do, it means it's not done. So the other thing is I could have that wrong. I've not got my glasses, but what I'm getting at is that would normally trip. Then you would come back, turn it off, reset it, turn it on, and then set this to your milliamps, all right? So you've got milliseconds, milliamps. The 2 tests were required on the paper defined as the milliseconds and milliamps of what it trips and what it should be doing. Okay, it's overloaded. Let's have a look. If I now change the value, so that's set to 10 milliseconds, I'm pretty sure. All right, we'll put that in, test. Right, it tripped in 21. That's where, so me having that set to 10 and it was on a 30 milliamp second, it's not working correctly. Do you understand what I'm getting at? Now, I'll turn this off, turn that to milli, turn it on again, press the time. Okay, does the same thing. So the 2 things we're testing is milliamp, milliseconds, but we must make sure that we have this set to the correct value. Does that make sense? All right, so they won't have these written down underneath like I used to have under here. You have to identify which one's which and set it to the correct one. This is exactly the same tester you'll probably use in the LEP. We used to have big fancy ones, but look, these are $200. They're worth every penny to buy. I reckon they're great value. Very simple to use and all that stuff. And I make sure that we get the value of the test button checking on the test. Okay? Any other questions? No? Okay, we'll leave it at that.